Salam and welcome everyone. So today we're going to be working on the question on the screen that says a certain gas obeys the van der Waals equation with A equals 0.76 m raised to the power of 6 Pascal divided by mole squared. Its molar volume is found to be 4.00 times 10 to the power of negative 4 meter cube per mole at 288 Kelvin and 4.0 megapascal. From this information, calculate the van der Waals constant B. What is the compression factor for this gas at the prevailing temperature and pressure? So this is a question from the physical chemistry Atkins 11th edition, and as you can see, this is just a standard question. But of course, there's a lot of information. So the first thing you have to do is to write out all of the parameters. We're told that the a certain gas obeys the van der Waals equation. So we're dealing with the van der Waals gas here, and we have the A value. So one of the van der Waals parameters to be 0.76 m raised to the power of 6 Pascal divided by mole squared. We know the molar volume Vm because they said it is 4.00 times 10 to the power of negative 4 meter cube per mole. We know the temperature is 288 Kelvin. So temperature is 288 Kelvin. We know the pressure is 4.0 megapascal, or times, you can just say times 10 to the power of 6 Pascal. Okay, that's what mega is. From this information, calculate the van der Waals constant B. So basically, with all the information we have to determine the value for B. We also asked to calculate the compression factor for this gas at the prevailing temperature and pressure. So we also asked to find the value Z. So yeah, that's it. Determine B and determine Z when you've been given all of this. Before we can go ahead, the first thing I want you guys to note is this. For a van der Waals gas, we have to use the van der Waals equations of state, which is just this information here, or this equation, which is P equals RT. So P as in pressure, R gas constant, T temperature, divided by the molar volume minus B, okay, minus the parameter A divided by the molar volume squared. So this is the equation or formula we're going to be using to determine B. First of all, we have to remember that we have the value for pressure. We're given that, so thank God. We have the gas constant because it's a constant. We have the value for temperature. We have the value for A. We have the value for molar volume. So all really what we have to just do is to substitute all of this information and to determine what B is. So yeah, that's how what we're gonna do. So let's start. So to find B, we can just rewrite the equation as P plus A over Vm squared, okay, equals RT divided by Vm minus B. So pressure would just simply be 4.0 times 10 to the power of 6. So megapascal, or times 10 to the power of 6 Pascal. But I want to quickly mention something. I'm not going to be using the Pascal when I'm solving this because Pascal is the unit for pressure and I cannot cancel Pascal out like that. So I'm going to be using Newton per meter squared, which is another way of writing Pascal. Of course, Pascal unit for pressure. Pressure is force over area. Hence why the unit for force Newton, the unit for area meter squared. So I'm going to be using this here, Newton per meter squared. So just make sure you note that because it's not going to be easy for me to be canceling out pascals. So let me put Newton per meter squared. Okay, that's how it's going to be for everything. So Newton per meter squared. So that's the units for pressure. So I'm just going to put PA here for Pascal so you guys know what's going on. So then you have plus A. What is A? We know the value for A here is 0.76. 0.76 m raised to the power of 6. So that's meter raised to the power of 6. And then Pascal. So I'm just going to say Newton per meter squared. Okay. Okay, that's another one. Per mole squared. So let me put per mole squared. Okay, divided by Vm squared. The molar volume squared, which is just 4.00 times 10 to the power of negative 4. 4.00 times 10 to the power of negative 4 meter cubed per mole squared equals R. So R is just the gas constant. We're going to be using this particular gas constant here. We're not going to be using the 0.08206. We're going to be using 8.3145. Okay, meter cubed. Okay, Pascal. But of course, we're not using Pascal. We're going to be using what? Newton per meter squared. Okay, per mole Kelvin. So per mole Kelvin. Let me write Pascal up here so you guys know what is going on here. Don't worry. Like when we're past this point, you guys will have more confidence. I'm just substituting. It's just that values are big, and the units are a little bit what they call it. It's a little bit complicated, but it's not hard. Anyways, temperature, we know the value for temperature is just 288 kelvins. So I'll put 288 kelvins here. So I'm done with the numerator here. I'm now going to say divided by Vm minus B. So the molar volume is just simply 4.00 times 10 raised to the power of negative 3, and then meter cubed, okay, per mole, okay, minus B. So that's it. That's really it. That's the first substitution. So now we try to break down information so that it's like easier for us to calculate. So that's what I'm going to be doing next. So yeah, that's what I'm going to be doing next. So rewriting this again, we have, let me change the color. Maybe it's going to be easier to, so that way we can easily differentiate. So you have 4.0 times 10 to the power of 6 Newton per meter squared plus 0.76 meter raised to the power of 6 Newton. So sorry, I apologize. Let me rewrite this. Newton per meter square. Newton per meter square per mole squared. So let me just say mole raised to the power of negative 2. Okay. Just to make things easier. Divided by 4.00 times 10 to the power of negative 4 all squared is just the same thing as 1.6 times 10 to the power of negative 7 meter. So m cubed squared is the same thing as m raised to the power of 3 times 2. So 3 times 2 is 6. And then mole squared is the same thing as mole times mole, which is just mole squared. Of course, you know that mole raised to the power of negative 2 and most and let me just rewrite this. I apologize. So m raised to the power of 6 per mole squared can also be written as mole raised to the power of negative 2. So yeah, that's it. So we can start like we can start cancel stuff out honestly. So you have mole squared here, you can have mole squared here. You have m raised to the power of 6 in the numerator, you have m raised to the power of 6 in this numerator as well. So I have made this part of our work easier. So I'm just gonna say equal to, let's go on to the other side, 8.3145. So going to the other side, I can say 8.3145 meter cubed Newton per meter squared times 288 Kelvin. So I'm going to multiply this value and this value together. And when I multiply them, because of course we're trying to make our work to be simplified. So 2394.576. Okay, we have the meter cubed Newton divided by meter squared. And then you have mole Kelvin here, and then of course you have Kelvin here. And what you can simply do is to cancel out the Kelvins. Okay, you can also cancel out m squared from m cube, would just leave you with m. So here what you end up with would be different. Of course, this is just the numerator, so I'm just gonna have divided by here 4.00 times 10 to the power of negative 3 meter cube minus b. So 4.00 times 10 raised to the power of negative 3 meter cubed per mole, okay, minus b. So this is the denominator. And I'm trying my possible best not to confuse you guys, honestly. So with time, it's going to be easy for you to like digest. So you have 4. So this is the next one. So you have 4.0 times 10 to the power of 6 Newton per meter squared, okay, plus 0.76 divided by 1.6 times 10 to the power of negative 7. When you do the division, you input 0.76 divided by 1.6 times 10 to the power of negative 7 in your calculator. What you end up with is 4.75, okay, times 10 raised to the power of 6 Newton per meter squared equal to 2394.576, okay, Newton meter per mole. So I'll write Newton meter per mole here. Okay. All of this information here divided by 4.00 times 10 to the power of negative 3 meter cubed per mole minus B. So that's it. That is it. I apologize. I know this is a lot, but you know, it's I don't know, it's chemistry. That's just how it is. So yeah, this is what you have so far. So let me rewrite this again to try and just so it's easier for you guys to digest. So you have 4.0 times 10 raised to the power of 6, okay, Newton per meter squared, okay, plus 4.75 times 10 raised to the power of 6 Newton per meter squared, okay, equals to 2394.576 Newton meter per mole, okay, divided by this information here, 4.00 times 10 raised to the power of negative 3 meter cube per mole, okay, minus B. So as you can see, this is better, but we can even make it much more better because we have Newton per meter squared here, Newton per meter squared here. From this, you already know that the units are the same, so we can just simply add up this information. Both of this information can be added up to have 8.75 times 10 to the power of 6 Newton per meter squared. Okay, so the left hand side is okay. And then 2394.576 Newton meter per mole divided by 4.00 times 10 raised to the power of negative 3 meter cube per mole minus B. So that's it. So yeah, we just simply cross multiply. And cross multiply, you just have 8.75 times 10 to the power of 6 Newton per meter squared times 4.00 times 10 to the power of negative 3 meter cube per mole. So we're going to multiply that one first. And when we do that first part, we have 3.5 times 10 raised to the power of 4 Newton meter per mole. Okay, that's the first part. Minus 8.75 times 10 raised to the power of 6 Newton per meter squared B equals 2394.576 Newton meter per mole. So that's it. That's literally it. Of course, because this one is has the value of B, we're gonna isolate it from this other information. We also have a situation where Newton meter per mole here and Newton meter per mole here. We can just do the addition, or we can just put them or group them together. So when we group them together, we have this situation where you have 3.5 times 10 to the power of 4, okay, Newton meter per mole, okay, minus 2394.576 Newton meter per mole, okay, equal to 8.75 times 10 to the power of 6 Newton per meter square B. Newton per meter squared, and then of course the B, our variable. So, of course, when you do this, you end up with 32, okay, 1,605. By the way, this is 3.4 times 10 to the power of 4, 3.5 times 10 to the power of 4, minus 2,300. So it's just basically 35,000 minus 2,394.576. So you're just going to end up with 32,605.424 Newton meter per mole, okay, equal to this information here, 8.75 times 10 to the power of 6 Newton per meter squared, okay, B. So, of course, you guys know what's next because you've been doing math your whole life as chemistry majors. Well, you've been doing math your whole life, and then for chemistry major, you should know this. You're just going to cancel both sides by 8.75 times 10 to the power of 6 Newton per meter squared in order for you to isolate and determine the value for B. So I'm going to do that here. So 8.75 times 10 to the power of 6 Newton per meter squared. Cancel out this, cancel out the Newton, cancel out the Newton here as well. Yeah, so those are the only things I can cancel out. So of course, when you input this information to our left in the calculator, 32,605.424 divided by 8.75 times 10 to the power of 6. When you put that information in the calculator, you end up getting 0.0037263. And then you've got meter, and then divided by 1 over meter square, will just give you meter cubed per mole. So this is basically the answer for B. Now, you're tempted, I can see, to just say, yeah, I got my answer, and now you move on. But the problem is this: whenever you're dealing with STEM related questions, especially chemistry questions, you cannot just determine the answer. You have to go back to the lowest number of significant figures that is in the initial question and use that number of significant figures to put your answer to put your final answer. So basically what I'm saying is, if you have three significant figures, that is the lowest number of significant figures in your question, that means your final answer has to be in three significant figures. In this case, our lowest number of significant figures is two, because we've got two significant figures here, three here, two significant figures there, three significant figures here, two significant figures. So we have to put our final answer in actually two significant figures. So it's going to stop right here. So I can rewrite this to be B is equal to 0.0037 meter cube per mole, or B equals 3.7 times 10 to the power of negative 3 meter cube per mole. So this is basically the answer to the value for B, the chemistry way, where the two significant figures are the only things we focus on. So of course we have determined B, but as much as you're like, "Yeah, thank God, finally," our work is still not done, because we're told to determine the compression factor Z. So the compression factor Z is just going to be what? Well, when you're dealing with questions like this, especially for van der Waals gases, and you have compression factor questions, note that the formula for compression factors when you're dealing with real gases is just PV M, so pressure times the molar volume, equals RTZ. Okay, where R is gas constant, T is temperature, and Z is compression factor. Hence, Z is just going to be simply pressure times the molar volume divided by RT. So that's it. So we're just going to say Z equals, we're going to substitute the value for pressure. So going back up top, we know the value for pressure to be 4.0 times 10 to the power 6 Pascal. So I'm just going to say Newton meter. So 4.0 times 10 to the power 6 Newton meter square, or Newton per meter square rather than Pascal, times the molar volume. We go back up there. The molar volume, we know that to be here 4.00 times 10 to the power negative 3 meter cube per mole. So 4.00 times 10 to the power negative 4 meter cubed per mole, okay, divided by the gas constant 8.3145 meter cubed, okay, Pascal, which I'll just say Newton per meter squared, okay, times temperature, which is just 288, sorry, Newton per meter squared per mole Kelvin. Forgot that part. And then 28, and then temperature is just 288 kelvins. By the way, the what they call it, the compression factor has no units, so you have to make sure you cancel everything out to make sure there aren't any units. Anyways, let's move on. So I have here I've got meter squared, I've got meter cubed here, so this will just remain 1m. I've got Kelvin here, I can cancel Kelvin here. I've got meter squared here, meter cubed here, this will remain in m. Since this remains m in the numerator and here also m in numerator, I'm going to cancel m again, I'll cancel m again. Of course, I'm going to cancel Newton because it's a numerator, as well as Newton here as well. You've got what's it called, mole in the denominator here, and of course you've got mole in the denominator here, so you've really cancelled out all of the units. Let me rewrite this. Z is not just the numerator, Z is everything here. So yeah, the value for Z is now going to be Z equals 4.0 times 10 to the power of 6 times 4.00 times 10 to the power negative 4. So multiplying the numerator, you end up with 1600, okay, divided by 8.3145 times 288 is just going to give you 2394.576. Of course, when you input this information further in your calculator, 1600 divided by 2394.576 will just give you 0.6682. So this is the compression factor. But then again, we're chemists. We cannot just use this as the compression factor, because it's just isn't enough. Like this, sorry, not that isn't enough, but it isn't the correct answer. So we go back to see how many number of significant figures, that is the lowest number of significant figures that we use in calculating this question. So looking at our work, we see that we have two sig figs here, three sig figs, three sig figs. So two sig figs is the lowest number of significant figures. So we're going to approximate our answer. And our answer is going to be in two sig figs. So Z is actually going to be approximately 0.67. So if you have any questions, please leave in the comment section. I'm here to help you and to answer whatever questions, concerns, or suggestions that you may have. I also wanted to mention that there's going to be another question very similar to this, and I'm going to be doing it on my channel as well. So make sure you stay tuned to watch that video as well. Just to give you a preview of what the question would look like, it's going to look like this. right here. Certain gas obeys the van der Waals equation of state, or equation with A equals 0.50 m6 Pascal per mole square. Basically, this entire question with the similar concept of the question we just did, I'm going to be doing it in another video. So make sure you look at the description box and also click the link to continue learning. Now we're at the end of the video, but I wanted to mention that if you're a student who is trying to succeed in all your STEM related courses, make sure you email me at shohabitutoring@gmail.com. I help students who are trying to improve and succeed in all your STEM related courses, whether you're in middle school, high school, or college, to succeed and to be the best version of themselves in their academic career. So if you want my tutoring or mentorship services, make sure you email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.